Hello and welcome to the 2022 Outback Joe Challenge Final Year Project. My name is Andrew Aldermoni and I'm gathered here today with Udeep and Ting. The Outback Joe competition is a number of teams competing from different institutes to locate and identify Joe, who is in need of medical assistance. Using the fixed-wing Javelin drone, we will make the necessary modifications to accommodate the mission's objective. Firstly, the motor is overpowered and hence too heavy. Aerodynamic optimization is required to improve cruise condition performance by installing detachable winglets. A flap system that will improve takeoff and landing distance is also required. Finally, a payload system that consists of design and manufacture of a rover, parachute and deployment system. The rationale. Aerodynamics requires a target of 10 to 15% increase in endurance due to the added weights from the added subsystem developments. In addition, the aerodynamics package includes streamlining the Javelin to further reduce lift-induced drag. Rover design and deployment. Joe, who needs immediate medical attention, requires a rover to communicate the state that he's in. Therefore, it is required to develop or acquire a rover that can function and overcome obstacles such as branches, rocks, or any obstacle that may impede the mission. Secondly, design or acquire a parachute system that is engaged when the rover is deployed. Propulsion. The existing power plant is overpowered and hence too heavy. The propulsion engineer therefore must perform the required calculations to develop a model that will justify or validate the selection of a new electric powered motor and acquire a new propeller using the same systematic approach for the motor. Project timeline. Each person has a set of tasks they need to incorporate into milestones that take a systematic approach. As shown, it is broken into two sections: planning, which may be design, research, and making sure that every task is feasible, and the second is carrying out the necessary method to further optimize the design, manufacture, and then finally testing to compare results with the intended expectations of the initial aims of the project. The methodology of aerodynamics is based on taking a systematic approach for each task that are specified in the project timeline. Figure 10.1 to 10.3 depicts a carbon fiber plate that was designed using the shape of the tip airfoil which was used for that segment of design and manufacture. Figure 11.1 to 11.3 is all the components coming together for the winglet design. The end plate is fixed to the carbon fiber plate, and the connection between the end plate and the winglet consists of a sliding extrusion of two pieces that are locked by a nut and bolt. Finally, the flap system, which as you can see is made up of a housing that holds a servo which is attached at the boom, not fixed to the wing but is in a rigid position that can be uninstalled at any time. The servo is then connected to all minor instruments that operate the flap system, such as the horns, control rods and hinges. Securing of the winglet inside the wind tunnel meant obtaining an interfacing circular spar and a force balance that could withstand 1,000 newtons. Setup for interpreting results consisted of calibrating the instruments that supported the wing by using pulleys and weights, and assigning a calibration factor where necessary. The test parameters matched the cruise condition boundaries of flight, which meant operating in around 70 km per hour and changing the angle of attack between -7 and 10 degrees. The graphs obtained through the 70 km per hour case depicts the variations in CL versus alpha, which showed an improvement of 9.7%. CL versus CD, a 19.6% in lift-induced drag reduction. Lift on drag versus alpha showed 12.7%, and CD versus alpha showed an improvement of 3%. Finally, the recommendations. Redesign and fabricate the winglets out of carbon fiber to reduce the weights. Gaining access to the necessary equipment such as a vacuum forming machine early on for cowling considerations. If not available, see to another method. And lastly, extend the flap system and build necessary components used for actuating. I will now pass you on to Udeep, who will discuss his part.
Thank you, Andrew. We'll start off discussing the rover from methodology. The methodology of designing the rover was a linear iterative approach where we would begin with the sizing constraints and then move on to component selection and then finally move on to prototyping. Prototyping would consist of testing the design for any flaws and making iterations to amend these flaws as we go on. And this process would generally be repeated until we would have a suitable prototype. Now moving on to the requirements of the rover itself. The general requirements the rover needed to meet were quite simple, and it needed the capability to travel over a typical farm terrain which would be predominantly gravel and soil. It also needed to be below the 2 kilogram weight limit of the Javelin's payload limit, and it needed to be able to reach the ground safely once deployed mid-air. There were 4 prototypes in total that we were able to design, manufacture and test. The first prototype used a track-based drivetrain, which was done to maximize the traction on the aforementioned rough terrain. This remained unchanged through the 4 iterations. However, the main changes were made to the suspension system, as we faced a few different issues. The first issue was with regard to structural integrity of the suspension brace in prototype 1, which failed on multiple occasions during transport. The second problem was with regard to bending and cracking of the main chassis, which we've seen in prototype 2. Prototype 3 also had issues with friction in the drivetrain, which caused the gears in the servos to skip. These were all addressed for prototype 4. However, the flipping mechanism that we introduced for prototype 4 is not yet functional. This may be attributed to the levering mechanism that's currently being used. That aside, the rover is fully capable of accepting a control board and beginning test operations. This final CAD drawing shows the full design of the geometry of the final iteration of the rover. The final step of the design process was parachute selection. The selection of the parachute was done in accordance with a guide for model rocket parachutes, which allowed us to use a payload, mass, and target terminal velocity for descent. This may cause issues in terms of parachute unfolding time, but was deemed a non-issue due to the flight altitude of the Javelin UAV. Some future recommendations include using the same high-torque continuous servos used to drive the tracks to be used with an appropriate gear system to overcome the torque issues that we faced with the flipping mechanism. The drive servos could also use a similar gear mechanism to avoid any sort of torque issues we may face in the future. In terms of testing could be improved by using an FEA-based impact model to remove wait times in 3D printing, and may make room for some design optimizations which would not be possible without FEA. And now I'd like to hand things over to Ting, who will tell you about the upgrades that were made to the propulsion system.
The propulsion system, the correct choice of aircraft propeller can affect flight duration. A light motor has been selected which can still prove enough power for the aircraft. An experiment for propeller selection will be set up. Propeller will be tested with forced airflow in wind tunnel to simulate performance evaluation during flight. Key indicators such as advance ratio and propeller efficiency will be calculated to determine the performance of the propeller. The test on the select propellers will be tested in RMIT Bandura Campus Wind Tunnel Lab. A 6-degree freedom force balance will be used in the test to measure and record thrust and the torque generated by propeller. The thrust generated by propeller is parallel to the airflow. In the test, a remote controller is used to control throttle to simulate RPM at a real condition of flying. There are 5 propellers need to be tested in this experiment. The propellers are made of 2 different materials. One is carbon fiber and the other one is plastic. The propellers have different lengths from 20 inches to 22 inches and different geometry pitch from 10 inches to 12 inches. Due to the aircraft's cruise speed is at 80 kilometers per hour, the result analyzing will firstly focus on speed 8 kilometers per hour for primary decision. The other airspeed will be used to show the performance curve of all propellers at a certain throttle level, and a final decision of selecting propeller will be made after all. Also, due to the power shortage during the experiment, the throttle is limited to level 4, which is 50% of the full throttle. By comparing all propellers from result 1, propeller diameter difference can make a significant difference on propeller efficiency and advance ratio at low throttle level. The 22x12 propeller has the best efficiency. Due to throttle level limited, for result 2, 22x12 propeller cannot give a bigger efficiency. Compare all 5 propellers at throttle level 50. 22x12 propeller has the best curve, which shows the propeller has the best performance. In conclusion, due to the power issue, there are some regrets about the experiment. Performance of some propellers cannot be fully tested, but the existing results are still satisfying. The problem for propulsion system is solved. The results shows a propeller with diameter of 22 inches and a geometry pitch angle of 12 inches is the best choice. The problem of motor is solved. A light motor is used, and the motor is able to prove enough power.
On behalf of Ting, Urdeep and myself, we'd like to thank you for watching and witnessing what we've accomplished as a collective and hope you enjoyed the presentation.